Hello there, this is Truth Socrates. Welcome to video number 31 for my series in multivariable calculus, known as Math 5C at Pasadena City College. So today's a big day. We're going to start a new chapter, chapter 5, and there we're going to see parametric surfaces and flux integrals. Okay, and you'll be happy to know that we'll be developing and constructing the last kinds of integrals that we are going to see in this class. So the end is in sight, so to speak. So I will see you on page 255. We'll do a brief chapter summary. All right, here we are. So it's going to feel a little bit like chapter 4. First, we're going to construct a new family of objects, and they're called parametric surfaces. Okay, so in the last chapter, we did parametric curves where we had r of t, but now we have two variables, u and v. So instead of a curve, that's going to create a surface for us. Okay, we are going to make a surface integral for a scalar function, and instead of dx, dy, or d little s, we have d capital S. Okay. We are going to find derivatives for parametric surfaces and construct tangent planes. Okay, we will learn how to find the area of a parametric surface, and if we pretend that a surface is like a shell, something like a ping pong ball or an eggshell, and we have a density function for that surface, we can find the mass of that surface. We are going to talk about orientable parametric surfaces, and I just finished writing up a rather long 5-page explanation why a certain surface that you might know is not orientable, but that's going to be coming soon, maybe 4 or 5 videos down the road. And we're going to find the flux of a vector field across an orientable surface. Okay, so these are the last two kinds of integrals that we are going to compute. And here are some pretty pictures that we are going to see in this chapter. So we're going to make a donut today, or something that looks like this. You take a circle and spin it around the z-axis, and that's called a torus, T-O-R-U-S. And yeah, here we have a tangent plane to a Cartesian surface. We're going to see one in a couple of minutes. And yeah, check it out. We're going to make tangent planes. So here's a normal vector at a point on a sphere. What is this snaky thing over here? This is called a helicoid. Okay, so we will see all of that, some of that in a few. So the good thing is that surfaces are not exactly new to you, because we have been drawing some fancy surfaces using the surface command in GeoGebra. Okay, so you already know this. There are 9 components to the surface command. You need the x, y, and z coordinates. You have 2 parameters, u and v. U will go from A to B. V will go from C to D. Okay, so the mathematical definition of a parametric surface is very similar. You have a vector valued function, not in one variable, but in 2 variables, u and v. Okay, u and v will come from some point D, a region in R2 on the Cartesian plane. Okay, and we will of course get as its output a vector in R3. When we graph that vector, we were only interested in the head of the vector. We don't draw the whole vector, unlike when we talked about vector fields a couple of videos ago. Okay, when we draw a curve, we only draw the endpoint of the curve. Okay, so when we draw a parametric surface, we are only interested in the endpoint of this vector, this output vector. Okay, so we associate with this vector the point x of t, y of t, and z of t. Okay, so it looks like I have a major typo over here. So those should be in u and v. Okay, I guess I'll make that correction in a couple of minutes. So let's take a look at our first example. Okay, we have Cartesian surfaces, right? We have functions where z is a function in x and y, okay? So another way to write that is, instead of x and y, let's call x u and let's call y v. Do we really need new variables? No, not necessarily, okay? So the x-coordinate is u, the y-coordinate is v, the z-coordinate is f of u v, okay? And u and v will be some region on the Cartesian plane, okay? So the easiest one would be a rectangle from a to b and then c to d, okay? So here's a function in two variables. It's just a simple polynomial, and we have a rectangle for the domain. So we have this parametrization, okay, u, v, and this function where we replace x and y with u and v, okay? And u is from -2 to 1, and v is from 0 to 4, our chosen domain. You can, of course, play with that, okay? So these diagrams were, of course, drawn with surface commands. And yeah, that's why I have the 10 and the 20 there, so that it's not too stretched out. If I don't have the 10, it'll be 10 times as tall, and it's not really very satisfying to look at. Okay, so of course, we know how to write the surface command for such a function. Okay, so now we are going to go to our workroom and GeoGebra. We are going to make ourselves a parallelogram. All right, so to save a little time, I wrote 4 points using our matrix notation in Scientific Notebook, okay, because we're going to perform vector arithmetic, okay? So we have these 4 points, and I am telling you that they form a parallelogram, okay? I want to create a surface command, essentially, that will construct this parallelogram for us, okay? Is it really a parallelogram? Why should you trust me, okay? So, well, let's connect these 2 points, all right? Maybe let's give them names. Okay, so here's A, B, C, and D. Okay, so are you really a parallelogram? Let's take a look at the vector from A to B. Okay, so we take B and we subtract A. Okay, and we get that vector. All right, great. So how about from A to C? Let's take C over here and let's subtract A. Okay, and we get a different vector. Okay, so well, that's natural because A is common to both of these vectors. Okay, so we get 2 vectors which are rooted at A. Okay, so now, how about the vector from how about B to D? Okay, let's explore that. Here is D, and we subtract B. Do we get something familiar? Ah, the vector from B to D is the same as the vector from A to C. Okay, so yeah, to be a parallelogram, sides have to be parallel to each other and of the same length. Okay, so of course, if the 2 pairs of sides are parallel to each other, then they are also forced automatically to have the same length. Okay, so how about what's missing? How about the vector from B to C? Okay, so here is C over here, and let's subtract B. And what do we got here? Ooh, that's different. Oh, okay, and that's because those are opposite corners of the parallelogram. It's like, wait a minute, I made this myself. Okay, so what else can we try? Let's look at the vector from C to D. Okay, so we have here C, D, and minus C. Are you gonna work? Will you look familiar? Ah, there it is. Okay, so AB is parallel to CD. Okay, Great. Let's go now to GeoGebra and see what a parallelogram looks like. Okay, so to save us some time, I already plotted the points over here. And yeah, you can turn it around as much as you like. And those 4 points, no matter which way you look at it, the sides should be parallel to each other. Okay, so we said A to C is parallel to B to D, and A to B is parallel to C to B. Okay, so that weird, okay, how come BC is not parallel to anything? It's not supposed to be, because they're diagonals of your parallelogram. Okay, so let's go back to our workroom and we'll make our parametrization, and then we'll come back to GeoGebra, input it, and see that we get the same surface. Okay, so yeah, we don't need B to C. We get these 4 pairs parallel, 2 pairs parallel sides, 4 sides, 2 pairs parallel sides. Okay, so AB and CD are parallel to each other. So maybe let's move them closer to each other. There you go. And AC and BD are parallel to each other. That's fine. So now, how are we going to make the parallelogram? Okay, so the idea is we're going to build on the idea that we use to create a line segment. Okay, we know how to create the line segment from A to B. That's just a curve. Okay, we take the vector from A to B, which we have already. That's our direction vector. Okay, so yeah, we did it before. Okay, so we said R of T is the initial point, which will be A, and then we will add a multiple of the vector from A to B. There you go. Okay, so of course we can combine that. Okay, so now what's going to happen? How can we form the rest of the parallelogram? Okay, well, imagine that you're somewhere between A and B, okay, along this curve essentially. Okay, the ruler right here. Okay, so you're walking along the line segment from A to B. Okay, you want to go to the opposite parallel side. Okay, so what do? You add the vector from A to C. Okay, except that will make you land to the opposite corner. Okay, not opposite, okay, but rather the adjacent corner to A, which is C. But I want every point in between. Okay, and that should sound familiar. Okay, because remember when we were drawing those fancy surfaces, I said think in vectors. Okay, you want every point in between, not just the final point. Okay, so that means we need a second parameter. Okay, that's why you have R of U, V. Okay, so I'm going to change this. I'm going to turn that into a U and that into a U. Not P, just U. Okay, so from each of these points, we will add this other vector from A to C, which is this. Okay, but we want every point in between. So that's where the V comes in. Okay, so of course, who are U and V? U and V have to be from a square. So U and V, element of 0, 1, cross, where are you? There you are, cross 0, 1. Okay, so the domain of this parametrization is just a square. Okay, so of course we have to combine these in surface to get our x, y, and z. Okay, can scientific note do that for us? Oh yeah, there you go. Okay, so it's 4u minus 3v minus 5, etc. All right, so that is what we are going to plug into our surface map. All right, so let's do surface 4u minus 3v minus 5, 2 minus 8v minus 7u, 6u plus 4v plus 3. U will go from 0 to 1. I will go, just kidding, V will go from 0 to 1. I said, woo, okay. It worked, it worked. So yeah, let's scoot over here. Yes, there you go. There is our beautiful parallelogram. Okay, so of course we can sketch it using the polygon command in GeoGebra. Okay, but of course we want to learn the surface command. Okay, there we go. So let's go back to our PDF and look at other examples. All right, let's talk about spheres. Okay, so we can use ideas from our discussion on spherical coordinates to parameterize a sphere, and this time it doesn't have to be centered at the origin anymore. Okay, now we didn't do this in our chapter on triple integrals because if your sphere is no longer centered at the origin, it can't be expressed as a spherical break anymore. Okay, of course we had that special case where the sphere was tangent to the xy plane, but that's the only other case we can that we can consider. Okay, when we're doing triple integrals. Okay, but if we're doing surface integrals, center can be anywhere. Okay, so for example, if we have this sphere, we could do the right half of the sphere just by adjusting the domain. Okay, if it were a full sphere centered at the origin and the radius is 4, we know exactly how to parameterize it. Okay? What do you have to do to adjust to the center? All you have to do is move x, y, and z to the corresponding center. Okay? So the center is at 2 minus 3 minus 1. There it is. All we have to do is add 2 minus 3 minus 1 to the 3 coordinates. And then, okay, check it out. We want the right half of the sphere. Okay, so will 0 to pi change? Nope, we still want 0 to pi. How about 0 to pi? Yeah, that will have to change because we're only going right half of the sphere. So instead of 0 to 2 pi, we only want 0 to pi. Okay, so keep the 0 to pi for the u, but adjust 0 to pi for the v, and adjust with a plus 2, minus 3, and minus 1. Okay, so let's go to GeoGebra and let's make, how about an upper half sphere? Okay, so now anything goes. So how about x minus 1 squared plus y plus 3 squared. Scary looking. Whoops, upper. And then plus, how about z minus 2 squared equals 4. Okay, not a very big sphere. Okay, so there we go. Okay, so what if we want only the upper half of that sphere? Okay, so the radius is 2. So let's start with, okay, so again, make the skeleton x, y, z. Okay, so let's pretend first it's centered at the origin. Okay, so we have two parameters, your phi and your theta. So u will go from 0 to pi, and v will go from 0 to 2 pi. Okay, so again, we don't need to use the Greek letters, otherwise you have to use the annoying keyboard. Ain't nobody got time for that. So the radius is 2. So let's do 2. Yeah, you remember your spherical coordinates? Okay. So x and y, do we need sine phi, cosine phi? I believe we need sine u, and then cosine v. And then for y, we have 2 sine u. Whoops, not times. Sine u, sine v. And then for z, we need 2, check it out, 2, I believe, cosine of u. Is that u? Yes, all right. So that is the same sphere. Oh, wow. It's like the Death Star or something collided with itself. So we have a sphere of radius 2, okay, but centered at the origin. Okay. So if I want that sphere centered over here, I want to shift to +1 minus 3 plus 2. Okay? But also, I want only the upper half. So what's going to change? Shall I give you a few seconds to think about that? What needs to change in our domain? Is U going to change? Is B going to change? Both of them, only one of them. Okay? Did you get the right answer? Upper half. You still need to go full circle around, but only halfway going down. So therefore that should be pi over 2. And yep, that's the upper half. And so adjust by the center, and we will have to do +1 over here, and minus 3 over here, and +2 over here. Are you right? Yeah, there you go. Scoot over. There you go. Huh, kind of look like someone had a haircut. All right, so that is our parametric surface. Yeah, we can hide, there. That looks more natural. Okay, so let's go back to our PDF and we'll talk about surface. One more thing before we go to Revolutes. All right, so let's do this next example. Find a parametrization for the portion of this paraboloid where y is at least 0. Okay, so yeah, the vertex is at y equals 4 and it's opening to the left. Okay, so let's go to GeoGebra, let's see what it looks like, and let's look at what part of the paraboloid we want to parametrize. Okay, here we go. So it looks like a bullet. Y equals 4 minus x squared minus z squared. Yeah, okay, so here's the x-axis, here's the y-axis. We want the part where y is greater than or equal to 0. Okay, so yeah, we want this part of the surface. Okay, so of course I input it as an equation, so we're seeing the whole thing. This extends to negative infinity on the y. Okay, but we only want this portion of our paraboloid. Okay, so how are we going to think about that? Well, that is the portion to the right of the xz plane, right? So let's draw y equals 0. Oh, there we go. Okay, so there is our xz plane. We only want the portion over here. Okay, and of course the key observation here is that we only want the portion to the right of a disk, this circle. Okay, the circle and everything inside that circle. Okay, so we get to think in polar coordinates. Okay, so that disk, we can parametrize it with r going from 0 to 2. Y is at 2. When y is 0, we get x squared plus z squared equals 4. Duh. So that's a disk of radius 2. And it looks like theta should go full circle 0 to 2 pi. Okay, so here we go. Surface x, y, z to be filled later. U is going from 0 to 2, and v is going from 0 to 2 pi. Okay, so U will take care of the radius, v will take care of the angle in polar coordinates. Okay, so now the thing is, oops, illegal command is because it's not complete. Go away. All right, looks like I have to stay right here. So the point I'm making is that we don't have a disk on the xy plane. It's on the xz plane. Okay, so we can choose x to be u cosine v, and not times but parenthesis, and it is z that will be u times sine of v. Okay, because our domain is on the xz plane. Okay, and so now y will be determined by the equation. So we will have 4 minus 4 minus x squared minus z squared. Okay, but let's do that in our head. X squared is u squared cosine squared. Z squared is u squared sine squared. We're adding them together and subtracting from 4. Okay, but cosine squared plus sine squared is just 1. So it's basically, did you get it? 4 minus u squared. Ooh, so there it is. Okay, so that is the portion of the paraboloid that we need. We don't need the whole thing. We only want the portion to the right. Okay, excellent. Okay, so for our final example, we are going to create a surface of revolution. All right, so let's walk through this example. Okay, we're going to make a torus by taking a circle and then spinning it around the z-axis. Okay, so we will center that circle at 0, 8, 0, and it will be on the YZ plane. Okay, does it have to be on the YZ plane? No, it can also be on the XZ plane. Okay, so if we want this to be a radius, then this will be the equation of the circle, ignoring the x coordinate. Okay, every point on the circle will now trace another circle. Okay, now because we're revolving it around the z-axis, the center of that circle will be on the z-axis. Okay, where will it be? Oh, at the height z sub 0. Okay, so it will be at 0, 0, z sub 0. Okay, and it will be located on the plane where z is z sub 0. Okay, so I have an example point for you here. If y is 4 and z is 3, then we get conveniently 16 and 9 are 25. Okay, so 0, 4, 3 is part of the circle. So let's check it out. Okay, so there it is. That's 0, 4, 3. Okay, that's the same point from another vantage point. Okay, so now we are going to take that point and we are going to rotate it around the z-axis. Okay, so that's what we're doing over here. Okay, so to do that, you could use the curve command. Okay, but we don't want curve. We want the entire donut, no sharing. We want the whole donut. We need the surface command. Okay, so what are we going to do here? Ooh, there it is. There's what we get using the surface command. Okay, so I develop it in 2 steps. Okay, so first of all, to make the circle of radius, what did I say? Radius 5, centered at 0, 8, 0. Okay, so you can use the curve command. We know how to make a circle even if it's not centered at the origin. Okay, so we use cosine and sine. Okay, the center is at 0, 8, 0. The radius is at 5. Okay, so I call that R1 of t. Okay, so now what do we need? This point is being spun around the z-axis, and the radius is controlled by the y-coordinates. Okay, so here is that point, and you can still see the orange circle where that point spins around the z-axis. Okay, so the distance from the z-axis is the y-coordinate of that point. Okay, so we're going to take this y-coordinate, that will be the radius of a circle going around the z-axis at the plane z equals this z-coordinate. Okay, so couple of things going on there. Okay, if you need to rewind the video, listen to what I said again, please do so. Okay, so now we are going to have a second parameter u, and that is what will generate the circle, again, using cosine u, sine u. Okay, so there you go. We can now put it all together. Okay, here is the x coordinate. The r is the y coordinate that we had before, with a cosine u, and the y coordinate with the sine u. Okay, so we have to change the current y coordinate to consider all the points generated by that single point with a circle. Okay? The z-coordinate stays the same. It's just phi of sine t. Okay? So, t and u both go from 0 to 2 pi. Okay? And we get torus. That is seen in our example. Okay? All right. So, for our final example, we have what's called a helicoid. Okay? And yeah, it looks like a helix and paraboloid put together. Okay. So yeah, how do you make a helicoid? You basically take a helix and you give it a thickness. Okay. So this is the more or less standard helix, except to save space, I put the trig terms on the y and z. Okay. So this way, it will spin around the x-axis, okay, rather than y-axis. Then we have a really tall diagram. Okay, I don't have that much space. Okay, so starting with the helicoid, you just multiply the two trig terms with the u. Okay, and you can be any numbers that you want, any range that you want. Okay, so here's an example. We have -1 to 1. Okay, one way you can think about it is, okay, you take, okay, where did I put my ruler? Huh. You can take a rod, okay, and spin it around its center, okay, and as you spin it around, okay, kind of like a baton, you walk forward, okay. So as you spin it around, okay, the points generate this helicoid. Okay, so there's the rod turning, turning, turning. These grid lines are, you can think of them as that rod. Okay, and it's tracing out the surface as you move walking along the x-axis. Okay, and if you change the -1 to 1, you basically just change the appearance of your helicoid. Okay, so here is another example where we have instead 0.5 to 1.5. Okay, it doesn't even have to have width 1. Okay, I can have width 3. Okay, it will just get wider and wider. Okay, so yeah, it kind of looks like a ribbon, don't you think? Okay, something that you might decorate a party with. Okay, party time. All right, so that is our video for today. We are going to take these parametric surfaces, of course, and we are going to construct surface integrals a little bit later. Okay, but after this video, we are going to look at the partial derivatives first of these functions, because check it out. They are now each functions of two variables. So you can take the partial with respect to u, partial with respect to t. What are we going to do with them? We're going to see in our next video. So until then, I hope you enjoy the rest of the day, and I will see you next time. Bye.